actually, physical design mainly you can divide into three categories: synthesis, PNR, and STA. If you are trained in PNR, physical design, you may be a synthesis engineer, STA engineer, or PNR engineer. Based on the requirement, based on your skill set, based on the possibilities, you may enter into any one of the area. Okay. So before that, you must be clear with your concepts. If you are clear with the basic concepts, then for you it is very easy to be in the physical design area. Like whenever they assign the project to you, like even in training as well, you come across various terminologies, various definitions. If you don't know about those definitions and you are directly entered into the synthesis, then you may feel some clumsiness. I'm very sure. For the same reason, before going to enter into the synthesis, it's good to have some basic fundamental classes. That is only the reason we are here. So let's get started. In first session, we have discussed about some basic terminologies like what are the goals of PD and how the technology is decided. What about the latest technology and all. Later we have discussed about ASIC design cycle, which is from market requirement or your idea to the IC, which involves various stages like RTL verification, RTL team, verification team, synthesis team, place and route team, STA team, and even physical verification team, fabrication and packaging. Yes. So we come across all these stages individually, and even we started about delay. Hope you know, between 2 points, a delay can be calculated by two elements especially. They are cell delay and net delay. Coming to the gate or cell delay, whatever the particular cell, is it a flip-flop or is it a AND gate or multiplexer or any other, either combinational element or sequential element, it has some particular delay. Like whenever you give the input, immediately you don't get the output. It gives the output after a certain period, and that is called cell delay. In a more professional way, in a technical way, we will discuss this cell delay as well. And afterwards we have net delay because of the interconnect or because of the metal wire. Hence, that net delay is also called as interconnect delay or metal delay or wire delay. So let's talk, we have discussed about net delay that causes due to three capacitances: fringing capacitance, area capacitance, and coupling capacitance. Fringing capacitance is due to the side walls, area capacitance due to that particular net, and coupling capacitance between the two adjacent nets. Coupling capacitance is more dominant. If the net length, if the overlap length is more, then the coupling capacitance will be more. So in order to fix that, we do routing. Actually, as I told you, the whatever the diffusion, ion implantation, oxidations, all present in the base layer, just like in apartment, in cellar. And in metal one layer, all the pins of corresponding those elements present. Means in first floor or ground floor, the pins corresponding to those oxidation, diffusion, ion implantation, whatever the elements present. So from that onwards, you'll get first floor, second floor, third floor, fifth floor. All those metal layers are in orthogonal fashion. That means you can see in the figure, right hand side, means M1, M2 are orthogonal. M2, M3 are orthogonal. M3, M4 are orthogonal. That means the successive metal layers are orthogonal to each other. The successive metal layers are 90 degrees to each other. In that case, the coupling capacitance is very less. You can see the figure. Whereas if M1, M2 are parallel, you can see the coupling capacity is more. So guys, as the coupling capacity is more, it gets affected on the delay. So to fix the delay, we considered both M1 and M2 are orthogonal to each other. So that coupling capacitance reduces, you can fix the delay. That is only the reason, guys. In our PD, whenever you entered into PNR, placement and routing in the sense, guys, it's very simple. Routing is connections. How you give the connections. Actually, there are two elements which are to be connected, which are present in the base layer. We don't apply the connections in the base layer only. No. Whatever the pins present in the M1, from that M1 starting pin 2 will go upward to M2, M3, M4, M5, and again we come downward M4, M3, M2, M1, and we connect the pin. So this is and all routing. In a single word, if you ask me what is meant by routing, it is connections only. How you connect between 2 points. Remember team, one more time, it is not routing, it is routing. The terminologies are very, very important. Even whenever you go to the PNR at the end, you will get engineering change order, ECO. Some people without awareness, they say echo. No, it is not echo. It is ECO only. Remember, this is also one of the very important observation. Like what I observed, like whenever I take interviews, people say echo like that. No. It is not echo. It is a ECO. Remember, team, the terminologies, how you use are very, very important. Okay, so it is routing. So coming to the definition, the routing direction in successive metal layers will be orthogonal to each other, perpendicular to each other. Okay, now guys, we are going to start the today's class. In this class, we discuss about Elmore delay and some fundamental definitions which we come across in later stages in synthesis, PNR and STA. And later on, we discuss about static discipline. Okay, these are the topics that we are going to discuss in today's class. This is our agenda. Now, let's get started for today's class. If something goes wrong, guys, and if I'm changing the slides, if you don't get, the slide is still Elmore delay only, please raise your voice, and I'll give you time at the end of the session. Still, if you have any doubts, you can raise at the end of the session. Still, it is disturbing you, the flow, then please raise your voice at any time. I'm here to clear your doubts, and I'm here to give comfortable. That's it. Okay, now let's come to the point. Guys, here, as I said, the interconnects, which is a metal wire. Yes, that metal wire or the connection, it could be a data connection or it could be a clock connection. Let us take here in a general, there is an interconnect having a length capital L. Then between this A and B points, there are some distributive resistances and capacitances. Remember team, distributive resistances or capacitances, you cannot access them physically. They are distributive, they are parasitics, they are intrinsic. Okay? So, here you cannot access them. Now, because of this resistance and capacitances, there will be there will be a delay, and that delay, like Elmore, a scientist, approximated in such a way that Elmore delay can be approximated as 1/2 RCL square. Here team, I'm genuinely, honestly telling you, the derivation is not required because you are not going for gate or you are not going for some other derivative field. So the derivation whatever is not required. Hence I am avoiding that, but I am giving you the conclusion based on the Elmore delay. Like he segmented, he divided the entire net length into different sections, and he calculated and he derived the formula, that is tau is equals to 1 by 2 RCL square. Here the noteworthy point is the net delay is directly proportional to the quadratic function of interconnect length. Okay, so here, do you want to reduce the net delay in you? Like as I said, in our design, if you want to optimize the delay, I am not saying if you want to reduce the delay. I am saying if you want to optimize the delay, as it is directly proportional to the like square of the length, why don't you split the length? Why don't you divide by connecting, by inserting one dummy buffer? You can reduce interconnect length. As interconnect length is reduced, you can optimize the delay. There is an enormous change, because if you reduce the length to a half, then it impacts more, because it is not directly, it is directly proportional to square of the length. So if you reduce the length by half time, it reflects out 1 by 4. So guys, here from this you need to understand one point. By reducing the interconnect length, you can optimize the net delay. Remember, this is one of the optimization technique that you will get in interviews. People may ask you, can you tell one delay optimization technique? As of now, remember, we come across only one optimization technique called buffer insertion. By doing buffer insertion, you can reduce the net length. Consequently, net delay can be reduced. Even people may ask you, there are delay optimization techniques. Can you tell one delay optimization technique which can optimize the net delay? That's none other than buffer insertion. That's it. Now, next, team, I want to concentrate on area optimization, subsequently power optimization, because team, if a design has more area, when you require more area, usually the design has more size, means more number of elements, then definitely you require more area. If the design has more number of elements, then definitely you require more power. Now, coming to the point, let's have this design. What it is doing, there are 16 full ladders, where 8 full ladders are adding both A and B bits, where A has 8 bits, B has 8 bits. It is adding both A and B, and there is a result. Similarly, there are C and D. We are adding them, and the lower full ladder contains C plus D value. The upper full ladders contains A plus B value. And there are 8 group of 2-to-1 multiplexers, which selects either A plus B or C plus D. So the sum, which is 7 down to 0, contains either A plus B value or C plus D value. This is what the design functionality. For this design, you require 16 full ladders and 8 multiplexers. Yes, you know guys, full ladder, let us take one full ladder. It requires one 3-input XOR gate, 3 AND gates, 1 OR gate, or else a full ladder requires 2 input XOR gates, 3 AND gates, 1 OR gate, which means the noteworthy point here, adder contains XOR gates, whether they are 2 input or 3 input, leave it. Adders contains XOR gate. You know, XOR gate has more internal logic. If you ask me AND gate, it is A into B. It is OR gate, A plus B. But whereas XOR gate, you see it is A bar B plus AB bar. Means to obtain that function, you require two NOT gates to get A bar and B bar. And you need two AND gates to multiply A bar B and AB bar. Finally, you require one more OR gate which represents A bar B plus AB bar. So what I am telling to you is, as XOR gate internal logic is more, the power dissipation is more in XOR gate because the logic is more. So that if XOR gate is present in a particular design, the power dissipation is more for that particular design. Hence we conclude, as XOR gates are present in the adders are the power hungry devices. In your design, if possible, try to maintain less number of adders. That is what the bottom line. And you know, in this design, as there are 16 full adders, the power dissipation is more in this design. So with respect to the area wise or power wise, it is not up to the mark. We are not happy. That's why you see here one emoji is not happy. He's showing his thumb in downward. He's not happy. So what we do? The tool is here to make him happy. How the tool can do? Here, the tool can do in such a way that the later design may require less number of full adders with the same functionality. Remember team, at the end, the functionality should not change. You can change whatever you want, but you don't have right to change the functionality. Now let's see the second slide team. Here you see, here the design you see, first we are selecting either A or C through the multiplexers, and there is one more like a set of 8 to 1 8 2 to 1 multiplexers B or D. These multiplexers select either A or C or B or D. Now 8 full adders are adding that either it is A plus B or C plus D only. So the full adders output is the sum which represents either A plus B or C plus D. So the same functionality, but still you only see how many multiplexers you require. 16 2 to 1 multiplexers, but how many full adders you require? 8 full adders. As I said, the full adders contains XOR gates. Adders are power hungry devices. Hence, try to see that your design contains less number of adders. Now you see, comparatively compare with the previous one, it is 16 full adders and 8 multiplexers. Now it is 8 full adders and 16 multiplexers. Yes, I agree. The multiplexer number is increased, but it's okay. Our concentration is adders. Our design must contains less number of adders. The second design contains less number of adders. So this design requires less area, so that the power consumption is, or the power requirement is less in the second design. So now the emoji is happy because the power dissipation is less, consequently the area is less. Hence we have given the conclusion team. The second design has less adders, therefore it requires less area, consequently less power dissipation. So in this way the tool can perform team. Okay, and this way of optimizing the area and the power, remember team, this method is called as operand isolation. Okay, I repeat, one of the power optimization technique or area optimization technique, that is operand isolation, because here you are isolating the operands. Hope you know in microprocessors and microcontrollers, you might come across this word called operand. The instruction contains opcode and operand. Move AX, BX. AX, BX are operands. Move is opcode. So coming to this, AX, BX are operands. So here also the data whatever you are isolating, you are separating. After isolating the data, you are adding the particular those data. Hence it is called operand isolation team. Okay. Now let's go to the another definition called logic restructuring. Team here, right hand side, you can see the tabular column which represents the functionality. If all the inputs are, A, B, C, D, E, the selection lines are 0, then definitely my output must be X6. If all the inputs are either 0 or 1, doesn't matter. If the A input is logic 1, then my output must be X1. This is my functionality. According to the functionality, yes, there is a design which requires 5 2-to-1 multiplexers connected in a cascade fashion in this way. Now you see with respect to the multiplexer operation, the functionality is, yes, it's okay. Because you see where A input is 1, the rightmost 2-to-1 multiplexer, as the selection input is 1, then definitely the output Y is X1 only. Yes, so the functionality is good. But the point is, the total delay requirement is, let's assume each one multiplexer requires a cell delay of 1 nanosecond. Then the total delay of the design is 5 into 1 nanosecond is 5 nanoseconds. But team, because of various reasons, I want to reduce the delay of this particular design to 3 nanoseconds. Let's assume. Then how can you do it? The tool perform logic restructuring to optimize the delay. Yes. What is that? Logic restructuring. How it does? It changes the architecture. That's what here team. The definition of logic restructuring. The reduction of delay without affecting the functionality of the design is called logic restructuring. Yes. Now let's come to the point. Here there are 5 multiplexers connected in such a way that, and of course it requires one more OR gate. You you verify, you get the same functionality only. The architecture has been changed, I agree, but the functionality is not going to, the functionality didn't change. The functionality is same only. Why to say? Why don't we prove? Let's prove. Now, team here, let's see that. See, this example I am taking. For example, A, let's take this as 0. Just a minute. Yeah, A0 and B0, C1, D0 or 1. Let's assume this is X and X. So team, here you see, first of all you take this A0, B0, C1, so that the OR gate output is 1. which is considered as a mux selection line. As selection line is input is 1, then this will go to the output. So ignore about this path. Now let's concentrate here. As the B selection input is 0, here you get X3. Similarly, as the selection line input A is 0, here the output of the multiplexer is X3 only. So the same X3 will appear at output terminal. Yes, team, this one. So this is about X3. So the functionality is same. We didn't change the functionality. So coming to the point, team, we have changed the architecture, but still the functionality is same. Now let us speak about delay. How much delay it has. See, parallel is going on. So till here it is 2 nanoseconds. And let's assume OR gate also 1 nanosecond. Then parallel is going on. This is 1 nanosecond. Then team, here this design requires a 3 nanoseconds delay only. So whatever the requirement, the design requirement, it is met. They asked us to 3 nanoseconds. Yes, we have changed the architecture and the delay is 3 nanoseconds only. This is called logic restructuring. Okay, team? Now, let's go to the sheet resistance. Team, here, if you take a particular cell and you take that particular cell geometry, physical information like length, width and all, that follows laws of resistance R is equals to rho L by A, where area is divided into width into thickness. For a given technology, the thickness is fixed, so that rho by thickness can be considered as sheet resistance RS, so that the resistance of a cell can be designated as RS into L by W, where RS refers sheet resistance, length of the cell, width of the cell. Now, team, from this definition, we understand the resistance of a cell is directly proportional to length of a cell divided by the width of the cell. Yes, team. Remember, it is directly proportional to the length, inversely proportional to the width. Now, let's have two scenarios. There is one cell called cell 1. Team, now you can, now in the slides you can see cell 1, cell 2. If not, please raise your voice. Otherwise, let's continue the process of learning. Now, cell 1, cell 2 are there. Cell 1 has 5 millimeters length, 5 millimeters width. Similarly, cell 2 has 15 millimeters length, 15 millimeters width. What we think in general, I'm not saying everyone, some of the people, of course, very few people think that the cell 2 has more dimensions, more width and length, hence its resistance is somewhat different. No, not at all. Because as the resistance is directly proportional to the length by W, if the length and widths are equal, in such case, their resistances are same only. Because 5 millimeter by 5 millimeter, 15 millimeter by 15 millimeter, they get cancelled. So definitely the length of a, the resistance of a cell 1 is equals to resistance of a cell 2. Remember, team, this is one important aspect. Now, let's go to one more definition called logic equivalence check. What is meant by logic equivalence check? Now, let's come to the point. To meet our goals, to meet our design requirements, we are adopting some of the methods. Let's consider this class only. we come across buffer insertion to reduce the net delay. We come across area optimization or power optimization, which is to like optimization technique for area or power. There is one more technique called logic restructuring. Because of these methods, the architecture or the extra devices, extra elements are going to be added into the current design. Then it's our responsibility to take care of functionality. Whatever you want to do, you can do it. There is no wrong in that. But still, we need to protect the functionality of the design. That is very important. So I'm not sure whether the functionality is same or not for the design obtained from the RTL team. Now the design of the present situation. So I want to check, and that check is called logic equivalence check. In logic equivalence check, let's consider synthesis, because I told you in physical design the first step is synthesis. So coming to the synthesis, that RTL team file, whatever the HDL file is the input, and gate level netlist is the output file. Guys, in synthesis you will come across all these information. So just for a while I am telling you, coming to the synthesis stage, input is RTL code, output is gate level netlist. And now you need to cross check with this RTL code and gate level netlist whether functionally are they same or not. You need to cross check, and that check is called logic equivalence check. Similarly, it happens to PNR also. If you are aware of PNR, then you can speak the synthesis output is PNR input only, and the revised netlist after post route stage will be the revised netlist, and you can cross check those two files as well whether they functionally same or not during PNR. And this check is called logic equivalence check, and the respective tools are conformal in Cadence environment, formality in Synopsys environment. But remember team, logic equivalence check is the mandatory check at every stage, which can be considered as a sign-off check. If someone asks you, synthesis has been done, can you tell what are the sign-off checks? Then please include this logic equivalence check. If someone asks you what are the sign-off checks after PNR, you please tell the techniques which we have to perform after PNR, but even include this LEC as well. Okay? And these are the very important definitions team. When you go to the interview, people will bombard you with these questions. So be ready. Okay? Now, let's come to the point. The next topic called the digital abstraction. Team, now nearly like we have reached some 50% of the session. Now we are going to the second half, digital abstraction. Are you with me? Please give me a some acknowledgement signal team. Are you with me? Are you there?
Yes, sir.
Yes, sir.
Okay, fine. Thank you. Now, let's come to the point, digital abstraction. Guys, why there is a necessity to go to digital? The God has given voltage or current. We have sinusoidal signals. Then why don't you be in the analog only? Why are you going for digital? Means there are advantages in digital. What are they? The advantage of digital systems team, they are very highly resistive to noise. Yes. Why? Because if you see the analog signal nature, it is quite oscillatory. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Minus 1, minus 2, minus 3, minus 4. Like that, it is quite oscillatory. But whereas digital, the signal you take either logic 0 or logic 1. Or else You see in another way, one person is having oscillatory mindset. He's studying BTech final year and is very much interested in core field, either he is a EEE or ECE. He is very much interested in core branch and he wants to work in core area, and he doesn't want to sit in front of the computer, means software. I'm not criticizing them, guys. At the end, your passion only. I'm talking about the person who is more passionate about VLSI. So he is preparing for core jobs, and all of his friends secured some jobs in software industry, and they are very happy, but he didn't get the job. And if he has oscillatory mindset, then if someone says, his friend or his faculty or his parents or his well-wishers, anybody, if they say one time, why you are wasting time in VLSI? It is not that much easy in VLSI. The entry is very difficult. Why don't you go to software? You just learn aptitude or reasoning. That's enough. You'll get a job easily. Or else you learn 1 month, 2 months course. There are plenty of jobs. People say if he's an oscillatory mindset, then immediately he will leave this VLSI field. He'll go to software. I'm sure he'll go to software, and he don't stay there. If someone says, why software? There is a recession because of war, because of so and so reasons. Why don't you go to government job? You try for bank jobs. If you get a job, nobody there to remove the job, to remove you from the job. If you tell something, then definitely move from software to again some banking. So what I mean is, the one who has oscillatory mindset is easily get disturbed by the other people. Let's see another side of the coin. There is one more person. Let's assume he has a stable mindset and he is preparing for a VLSI core job, and he is struggling a lot. He is searching and is not getting the right opportunity. He studied already, he trained already in PD, but he is looking for the opportunities. Industry is not good for various reasons. No one is giving the opportunity, at least interview. He is waiting for the interview, and his all friends hired by all the software companies, but still he never give up because he has oscillatory mindset, and his mindset can tell, it is your dream job. No, why don't you wait for some time? Great things takes time. Remember time. Remember team. I repeat, great things takes time. If it is a great thing, definitely takes time. It never happen in a single night. And don't think things happen in a single night. If it happens single night, it could be some scam. That is stand from my side. Okay. So coming to the point, if he has an oscillatory mindset, he don't go. He won't go. He'll try till he gets success. In the same way as the digital signals have stable amplitudes, for the noise it's very, very difficult. I'm not saying that is impossible, but that is difficult. Similarly, as they are possible to optimize to reduce the size and all, yes, scalability is present in digital, but whereas in analog that is not present. Moreover, programmable. Team, let us take one washing machine. You can dump the clothes. You can fix either blanket mode, jeans mode, fast track mode, or high genuine mode like that, and you can do your work. Once the washing, everything is done, the washing machine will play music so that you can understand the work has been done. Then you can go to the washing machine and you can remove the clothes and you can hang it to become dry. That means there is no necessity to stand near the washing machine. Washing machine, are you doing or not? Please do it. I have other work. Please do it. So that monitoring is not required. That the same thing happens in digital. In digital, Once you write the code, once you dump the code, you can do your work. This itself machine can do the task by itself and will let you know the result. That means automation. Automation is possible in digital systems only. That is not possible. That is never possible in analog. Remember, team. And one more thing. In analog, do we have memory? No. We have diodes, transistors, NPN, PNP transistors, FETs, MOSFETs, operational amplifiers and all. Let's have the analog domain which doesn't have memory. What do? No, you can't do it. But whereas in digital, we have some digital systems who has memory facility. I'm not saying all the digital systems. Even though combination circuits are digital systems, they don't have the memory capacity. Remember. But whereas sequential elements, memory, RAM, ROM, and all, yes, they have memory. You can dump the code. You can have the automation facility. Hence, guys, some of the digital systems have the memory facility so that you can store the data and you can retrieve it back whenever you need it. Hence, we conclude the digital systems are very much needed over analog systems. Yes, that's only the reason we are going for digital systems and we are not with analog systems. Yes. See guys, let us have the another perspectiveness, because how you see the design is your view, but you don't know how the other person think. His perspectiveness you don't know. You need to see in his perspectiveness also. Let's have digital design. Till now I have given you so many advantages and we are very sure and we are very proud of digital systems. Claps. Yes, fine. But is there any limitations? Yes, there are limitations. What are they? Team, here, if you want to adopt digital systems, you need to convert this analog data into digital. If your output device is analog device, then you have to convert this digital data into analog. Then in digital systems, you require ADCs and DACs. Analog to digital converters, digital to analog converters. That is extra burden to you. And if it is analog, you can work at higher power levels. Yes. For example, let's take half wave rectifier or full wave rectifier, bridge rectifier, which is a analog circuit which can operate till maybe till 20 to 30 volts. But whereas you take one digital circuit is a take microcontroller 8051 which can work with the voltage only 5 volts. If we give more than 5 volts, that IC gets damaged. Yes, here only 4 elements is working with even 30 volts, but here there is a big architecture. There are so many elements and all, but they work only with 5 volts or more than, around 3 to 5 volts. That means, remember team, you cannot work at high voltages in digital. If you want to work at high voltages, then please go to the analog. Go to the analog systems. That's why team, in some designs where you require analog systems and digital systems, those systems we call them, where both analog systems and digital systems are present, those designs are called mixed signal designs. So there are 3 types of designs: analog signal design, digital signal design, mixed signal design. Remember team. Okay. Now let's come to the point. This is the last topic in today's class. Of course, it's a big topic as well. Noise margin. What is meant by noise margin? Why there is a necessity to discuss noise margin? This is not any BE class, academic class, taking noise margin and all. No need. But why? Why are you taking noise margin? Now, the point is, team, here you know very well, nowadays you are getting the designs with 1 million number of gates, 1 million number of standard cells. See, even though you are taking CMOS technology, where the power dissipation, static power dissipation is very less, there is about power dissipation, there is a quantity of negligible leakage power also. When it is about only 20 gates, the leakage power is less. But when it is a 20 million gates, then definitely there is a considerable leakage power. Then how you optimize it, how you fix it, that is only the point. For that reason, we are studying noise margin. The question is, team, because of the external noise, there will be disturbance in the design. That disturbance is very minimum when the design size is 20. But the disturbance is maximum when the design size is 20 million gates. For that reason, we are discussing about noise margin. Now, it is a very easy concept, team. You love it actually. Now, come to the point. Let us take one analogy. Let's have why always boys example. Let's take girls examples. Please don't mind, team. Here there is no any gender difference. Just I am taking the example. That's it. One girl has less resistance power. Usually she have the food at home only. But whenever the food is not ready or she is getting late to her college, then she went to the college without having the breakfast. In canteen or any at the outside, because of hungry levels, she ate some food. Either it is vada pav or it is poha or it is Mysore bonda or anything. When she ate, suddenly she got stomach pain because of the other oils what they have used at their canteen or outside. That means we can easily tell she has very less resistance power. For the external something, her body is not like opposing. Simply it is get affected by that particular ingredient. Yes. Let us take one more girl. She's a foodie actually. She try the food at various places. If it is a new place, she will check in Instagram or Facebook. Foodies where like these are the good restaurants, and she go there every week. Whenever she find the time, whenever her papa has given the money, she go to the restaurant. She eat yummy food. Now the other one who is besides her think, she has so much of resistance power, man. Always she ate food at outside. Nothing happens to her. She has so much of resistance power. If anything happens in a bulk manner as well, nothing is going to happen. Nothing is happened to her. People use these words. Now with the same analogy, now we are considering the noise margin. Coming to this team, in a design, because of the external noise, there might be disturbance in the cells. There might be disturbance in the functionality. What is that? How much it can happen? If you want to fix it, what to do? All these things, for all these questions, now we are going to get the answers. First of all, the noise margin, coming to the definition, it is the maximum allowable noise voltage that can happen to the particular device. Even then, the cell output or functionality is not going to change. Sir, nearly 0.75 volts of noise is added, sir, but still output is fine. I didn't get any fault in the output. Yes, that cell has more resistance. It is more immune to noise. It has more noise margin. Even then, noise is included. Even then, Nothing is happened to that cell. That's what noise margin. So team, here, let's assume a particular cell has 1 volt of noise margin. Till 1 volts means the noise of 0.25, noise of 0.5, noise of 0.75, noise of 0.99. That much noise is included. Even then, nothing happens to that particular cell because it has a noise margin of 1 volt. If there is a noise signal from the external environment about 1.1 volt, then the cell functionality will be changes because it exceeds more than his level, his or her level. His maximum capacity is 1 volt. Less than 1 volt, if the noise happens also, nothing will happen. But whenever, if it happens more than 1 volt, then definitely there will be a change. That's why we conclude that for a particular cell, the noise margin must be as maximum as possible. That is bottom line. That is like the conclusion. That's it. So remember team, for a particular design, the noise margin must be as maximum as possible. That's it. Now, see team, as it is digital, we think from the books, the maximum value is 5 volts, minimum value is 0 volts. 0 volts is logic 0, 5 volts is logic 1. Now, coming to the point. Here, present technologies are working from 2.1 to even 3.5 volts. So nowadays, even you can see in the designs who are packaging engineers or hardware engineers, you ask them, their operating max voltage logic 1 is either 3.1 or around 2 or 3, I guess. But it is in between only. So, team, here, in digital, let's take for logic 1 max is 5 volts. Sir, if it happens 5.1, you tell me, sir, oh, what is that? In digital, max is 5 volts. Let's take your exam. The maximum points are 100 marks and you have written choice and all your answers are correct. Will you get 120? No, right? You'll get 100 only now. In the same way, here also, because of the noise or some other reason, if you get more than 5 volts, which is a 5.2, then definitely the system can understand and it takes as a logic 1 only, like 5 volts only. Means during logic 1 transmission, if positive noise is included, nothing happens. So positive noise is not affecting the logic 1 transmission. Suppose there is a negative noise, minus 0.5 volts, then 5 volts 5 volts minus 0.5 volts, you will get 4.5 volts. Whenever the receiver receives 4.5 volts, it gets in a dilemma. Arey, they told me for logic 1 5 volts now, but I received 4.5. What to do now? Now it is thinking at a particular state, it may consider it as a logic 0 or it may take it as a invalid state. There is a chance. Hence, we conclude that during logic 1 transmission, negative noise is going to be affecting the logic 1. Similarly, positive noise affects the 0 transmission because 0 is there. Whenever the negative noise is included, you'll get minus 0.5. So minus 0.5, you don't get it. So the system can understand as a 0 only. Similarly, whenever the positive noise is included, it is plus 0.5. Then the receiver receives the 0.5 volts, the signal, then it is in a dilemma. There is a chance of misreading the output. So the note is negative noise impacts logic transmission, positive noise affects logic 0 transmission. Now let's see the very important diagram, noise margin. Now you see team here, there are 2 buffers. The first buffer is a driver element or source element. The right hand side buffer is driven element or destination element or receiver element. Now you see the left hand side buffer is transmitting, so that it can be considered as output. So what is the minimum output voltage to be considered as a logic 1? What is the maximum output to be considered as a logic 0? They are, you see team here, just a second. Yeah, you see team here, this is VOL. I'm talking about this output only team. This is logic 1. Coming to this logic 1, what is the minimum voltage that must be there to satisfy logic 1? Means this is VOH. VOH is the minimum output voltage for logic 1. This has been written here. The minimum output voltage for logic 1. Similarly, what is the max output for logic 0? Then it is VOL only. You see here, VOL. That's why team, for this driver cell, the minimum output for the logic 1 is VOH. The maximum output for logic 0 is VOL. Now, here you see there is a driven element. Now, let's speak about there is a external noise happens between the driver cell and the driven cell. Guys, when we are discussing about PNR, I guess team, the speaker, the trainer will cover what are the sources of noise. If you ask me right now, I can say that is because of OCV, because of the crosstalk, because of so and so reasons. But here, as you are at the beginning of physical design concepts, not required, let's assume because of the external environment. So here the noise is included. That noise might be either positive or negative. Remember team. Okay, so positive or negative. Now let's come to the point. This is my value VOH. Let's take this VOH. That is, let's assume 4 volts. Now, as I told you, during logic 1 transmission, the negative noise may get impact. Because of the negative noise, let's assume 1 volt of noise. If it is positive noise plus 1 volt, negative noise minus 1 volt. Because of the minus 1 volt, here the driver element, the receiver element is getting the output as 4 volts. Then the driven element is in a dilemma. What they told us more than 4 volts is logic 1. No, but I got 3 volts now. Okay, chalo, take it as a logic 0, or it is a prohibited region, intermediate, indeterminate region, like that. No, the cell has some noise margin in such a way that if it has noise margin of, for example, 1.5 volts, then team, if it is included 1.5 volts, that will be the VIH, the minimum voltage required for the driven element, which can be considered as logic 1. Sir, because of negative noise, my value got reduced, sir. It's okay, man. It's okay. But we have your noise margin capability now. How much it has, sir? I have 1.5, sir. So don't worry. Till the noise is beyond 1.5, no problem. The system will understand, will detect, will recognize your output as it is. So, as the noise margin is 1.5 volts, sorry, As my noise margin is 1.5 volt, the noise occurrence is only 1 volt. Na? The system can detect 3 volts as a logic 1 only, because you see here this is the minimum. Okay, so this one, how much it can means, this one guys, this is noise margin high. This noise margin is high means VOH minus VOL. Similarly for noise margin low also, which is VIL minus VOL. Guys, as I told you back, the noise margin must be as high as possible. That means NMH must be high, NML must be high. To get NMH must be high, what are the possibilities in this equation team? Two aspects. Either VOH must be maximum or VAH must be minimum. Similarly, either VAL must be maximum or VOL must be minimum. Like this guys. So here remember, suppose if the noise margin for high, noise margin for low are different values, then you need to consider the minimum one. Means the worst case possibility where you get both the values means in minimum noise margin value only. So remember, in your like interview or whenever in your written test, for example, let's assume whenever you get the noise margins are different for high and low, please take the minimum noise margin as a design noise margin. Okay, so you take the order. The first one is noise margin. Just a second. Yeah, here the first one and the second one and the third one and the fourth one. So topmost must be VOH and the leastmost must be VOL. That is here I have written VOH, VOL. Okay, this must be the hierarchy. Remember guys. Okay, now let's have one aspect guys, static discipline. Coming to the static discipline team, if you give a valid input to that particular design, it must give valid output. This is what static discipline. Team, remember, if you are constructing a home, you won't manufacture bricks. Remember, you'll get the bricks from outsider, right? From any vendor. Yes. Similarly, whenever you are designing like your product, some of the elements and you don't manufacture it. Those who manufacture, who give them, like they are called vendors. We'll get the quotation from the vendors and we see the possibilities, what are the best fit, and after convincing of budget, we will take one of the vendor. Yes, here let's assume our design follows one static discipline and we want to hire some of the elements from the outside vendors. Now you see there are 3 vendors here. Designer, this is our designer, sorry. Here 2 vendors are there. There is vendor A, vendor B. Now whom you can choose? Can you take vendor A or vendor B? How you can choose? Provided it satisfies the static discipline. Yes. Now let's take noise margin high. For understanding purpose, I am writing guys. Noise margin high is equals to VOH. Sorry guys. Sorry for the bad handwriting team. VOH minus VIH. Similarly, nice margin low, VIL minus POL. These equations are mandatory, team. That is only the reason, even though it is difficult, I am writing. Now you see, team, here vendor A. See, for us, designer is very important. It is VOH. Sorry, it is 4 volts. That is VOH now. So whatever the vendor you are accepting into your design, those vendor VOH value must be maximum. Then only nice margin is high. In another case, to get high nice margin, you can have less VIH. Similar, to get high nice margin, VIL must be maximum or VOL must be minimum. Now let us see. Here the minimum requirement is 4 volts. As it is VOH, VOH must be maximum. So I'm expecting a value more than VOH, more than designer value. Here you see 4.1 is there. Fine, we want more. Here it is more than VOH is satisfied. Now let's take VIH. VIH must be minimum now. The designer value is 3 volts. So you need less than 3 volts. Here 2.9. So satisfied. Similarly 2 volts. VIL must be maximum. So more than 2 volts is accepted. Yes, satisfied. Similarly VIL must be minimum. Minimum, satisfied. So team, in vendor A, all the cases are satisfied. So you can choose vendor A. Nothing will happen. Similarly, go for vendor B, because one more vendor is there now. Similarly, here 4 volts, here 5 volts is there, we want maximum. Yes, 5 volts. Less than 3 volts is required, VIH. So 2.8, fine. More than 2 volts is required, 2.2, fine. More like less than 1 volt is required, it is 0 volts, fine. So guys, vendor B is also satisfied, but guys, you only tell me here, what is the nice margin here? Here, the nice margin is 1.1 volt. 2.9, sorry, 1.2, no, sorry. 3.9. Similarly, what is the nice margin here? It is 1.9. Okay, again 1.2 volts. Similarly, here you see team, here 3.8, 4.8, so 2.2. Whereas here you see, it is 2.2. So guys, as vendor A, vendor B have satisfied all the requirements, but still we can choose vendor B because the vendor B nice margin is good, is high. That's why team, the conclusion is vendor B has high nice margin compared to vendor A. So you can choose vendor B. That's it team. It's very simple. One more thing, even though for example vendor B has high nice margin for NMH, but NML is very less, then you need to consider the less one, smaller one only. And of course the budget is also important. If vendor A is coming for a very, for a less price, you can go with vendor A also. It is not always high nice margin only. It is about budget also. It is about finance also. You must have financial discipline as well. Your papa has given money from his sweat. Okay. Don't move him to to his blood. That's my sincere advice to you, to my buddies. So team, remember, you and me, everyone must have financial discipline. Finance is also important for any organization. Remember. Now, are you with me, everyone? Now, it is an assignment to you. We have given you designer values. Now, there are three vendors, vendor 1, vendor 2, vendor 3, and you only take a paper and pen, and you please suggest me through which vendor I can go. I am the designer. You please guide me, team. Take pen and paper. Yes, team, all these slides will be uploaded in our app. You can view them, and for more information, you can contact Rajat. Okay? And still, if you have doubts also, you just post to his WhatsApp account, and he will forward the same to me, and I'll update you. Now, the floor is yours. I'm giving you 5 minutes of time. Now, Alovika, can you justify your answer? Why you have chosen vendor 1? You can unmute yourself and you can justify your statement.
Because here, sir, VOH is 4.5, that is designer to height, and VIH is 3, that's it is same, and VIL also same, and VOL is 1 here for designer, and the vendor 1 is 0.5 because it is less.
Okay, good. And you tell me, Alovika, is vendor 1, as vendor 1 satisfied all the requirements, I mean in 4 aspects, can you tell what is the nice margin of vendor 1?
First one is 1.5.
Just a second. 1.
First one is 1.5.
Okay.
And second one is 1.5 also.
So what is the nice margin? You need to consider the minimum of both. What is the minimum value? Hmm, 1.5 only, no?
Yes, sir.
Now take vendor 2. What is the vendor 2 nice margin?
It is 1.3.
1.3. Okay. What about vendor 3?
And it is 3.5.
Actually, sir, for vendor 2, first is 2.3 and the second noise margin low is 1.2. So minimum will be 1.2 for the vendor 2.
Okay, 1.2. Yeah, 1.2. Good observation. Good. May I know your name?
Mini, sir.
Mini. Okay. Good, Mini. And Alovika, continue. Vendor 3.
First one is 0.8 and second one is 2 and the minimum is 0.8.
Okay. So what is the vendor 3 nice margin?
0.8, sir.
0.8. So vendor 1 1.5 volts, vendor 2 1.2 volts, vendor 3 0.8 volt. Right?
Yes.
Team, here the observation is, we know very well, VIH value must be, to get high noise margin, it must be small, right? Here designer value is 3 volts, but in vendor 3 the value is more than 3, that is 3.1. So he is not eligible. So don't take his file. If you take his file, as he is coming for lesser price, the business people may hire vendor 3. Then your design is going functionally invalid, the people may blame you because not satisfied with respect to VIH. So team, here what we are telling you is vendor 3 is not eligible. Either you can go with vendor 2 or vendor 1. As vendor 1 high noise, as he has high noise margin, for the designer we can propose vendor 1. This is what the conclusion. Okay team, this is what the conclusion. This is what for today's class team, and we catch up again in another weekend, and we'll continue the remaining concepts. There are nearly 5 modules team. If you follow all these 5 modules, then it is a good to go signal. You can rock in synthesis, PNR and STA if you know all these basic terminologies. I'm sure and I'm very confident. So don't miss the classes, and definitely you love whatever you desire. Okay, love your job, love your passion. So don't think about the other people, what they think, whether they got job or not. Leave it team, it's your journey. At the end you only there, not me or someone else. Okay, so great things takes time. Work on your dream job. That's what I want to tell you. Now it's a questionnaire session. Do you have any questions?
Sir, what are the sanity checks after importing the design to PNR?
Through PNR. Now coming to the team, coming to the question team. First of all, the beginners who are attending this class team, you please ignore this question because we don't know about synthesis and PNR. Now those who know this what we call PNR and who have trained already, for them, yes, you can attend this question. Coming to the question, team, sanity checks. You might come across this word called sanity. There is a sanity inspector. He went to that particular restaurant and he checked all the utensils. Is there like any genuine thing, or they are giving like 2-3 days milk or some other some waste food like that. So he is inspecting whether they are correct in a correct format or not. In the same way, sanity checks can be performed at any stage. Don't think it is at PNR or synthesis or STA. Even in synthesis also you can perform after elaborate, after synthesis, after any stage. Similarly for PNR, STA as well. Now coming to the sanity checks, what you can check, if it is synthesis, you get the input from RTL team, which is a RTL code. Whether the code is in a correct form or not, whether it is a bug free or not, whether it is an error free or not, it's important to you. If you get a wrong design and you are doing synthesis, it is a waste of time now. So you need to check whether you get the right design or not. Similarly, the topmost guy, the top level guy might have written .sdc file. There are some constraints which they may not met. In such case also, there might be some timing violations. So you need to check timing as well. Similarly, if it is PNR, it requires .lib files, .left files. And you need to check whether there is a correlation between the lib file and the left file, because lib file contains timing information, left file contains physical information. In lib file there is a cell, but that cell physical information is not available in .left file. Then that is not correct, no. So there is a correlation between .lib and .left files. For that you need to do check library. So there are 3 sanity checks present based on your stage. They are check design, check timing, check library. Of course, during synthesis, logic synthesis, you don't require .left files. then no need to perform check library. But however, if it is PNR, you require .left files. Hence, you can perform check library. So there are three checks: check design, check timing, check library. Of course, the syntaxes are different based on the environment. If it is a cadence environment, check underscore design. If it is synopsis environment, check design where D is capital. Like that, syntax could be different. Now coming to the question, team, whatever you asked, coming to the PNR, you have taken all the input files, whatever you require. Afterwards, see, you don't trust synthesis team. The synthesis team might performed well. They have given the right like a file to you, but please don't trust anyone. Even you don't trust Abhiram sir also. You must have your own way. So whatever the synthesis file output that they have provided, you take them and you perform sanity checks. What you can do? You perform check design, check timing, you check .sdc file as well, and check library, so that according to the design they are correct, like they are in a correct format or not. Including that team, remember the design must be clean from zero wire load model analysis, because in synthesis we assume the wire delays, the net delays are zero, but whereas here you are going to connect the interconnects, you are performing routing so that net delays will be introduced. For that reason, minimum of minimum, you must satisfy zero net delay. It must be clean. Even zero net delay is also not clean, then you cannot do anything. You just pranam karo to synthesis people, you give the file to them. That's it. You can't do anything. You cannot perform PNR. If you perform also, it is waste of time. That's it. See, if zero wire load model timing analysis itself is not clean, then again you are introducing the wire delays, then how come you get man? Tell me. So you need to perform zero wire load model timing analysis. That must be clean. That is the good signal. That is a signal to go to the next step. Either it is a floor planning or placement or whatever. If you want to go to the floor plan, in sanity checks, there must be a clean regarding the zero wire load model analysis. That's it. These are the sanity checks we perform before going to the floor planning. That's it. Okay. I think I have reached your expectation and you are satisfied with the answer. Is it?
Okay, sir.
Yeah.
So for physical synthesis, we have to give def file.
Yeah. Good.
How to give that def file in design compiler, sir?
Design compiler. Yeah, see team, see one thing I want to tell you, because here some people are entry level people are also there, but still I'm responsible for your questions. But what I want to tell you is, see, first of all, coming to the synthesis, there are two types of synthesis: logic synthesis, physical synthesis. As I said, in logic synthesis, we are least bothered about their placement details and all. But in physical synthesis, what we, like just now I said, in synthesis, you don't require .left files because we are not bothered about placement information. But whereas in physical synthesis, where we require placement information as well, we have the placement details as well. For that reason, you require .left files. So if you ask me what are the input files required for logic synthesis, I say simply tool license, RTL code, .lib file, .sdc file. That's it. But whereas if it is a physical synthesis, I require tool licenses, RTL code, .lib files, .sdc files, .left files, and team def file as well. So what is def file? design exchange format. In PNR, at every stage, the output is in def format only. So whatever, like whenever you perform floor planning, then immediately that output, the floor planning def, because in floor planning, whenever you are placing the macros and all, you don't require .lib files over there. Simply you are placing them, right? So you do floor plan with the .lib files, and you take that floor plan def and you give to this physical synthesis as a input. Now in this physical synthesis, we have timing information, physical information, and we have these placement details as well, so that this you can perform synthesis in a great way. So if you ask me, sir, logic synthesis, physical synthesis, which one has more accuracy? In physical synthesis, you have physical information as well, right? So physical synthesis is more accurate than logic synthesis. Okay, so this is about physical synthesis. And if you want to know much more about the physical synthesis, and with respect to the whatever, either it is GNS or DC, design compiler, that you see with respect to the tool there, it is not the correct signal to open whatever. Sorry team. Okay, I convinced you maybe up to 30 to 40%, I agree. But you get more details whenever, like we have our own roadmap, we have a clear vision. So let us complete all these 5 modules. Like they don't take much time, team. Remember. So in a short while we'll complete and we go there, and that particular trainer will discuss that particular things definitely. Okay. Or else we have a separate doubts clearing session. There we will discuss. Sure. Please bear for some time. Okay, it's 1 hour 45 minutes. Okay, team, if you have any doubts still, please approach Rajat and he will coordinate with me, and you will get the answers. Okay. So finally saying a simple thank for your valuable time. Please don't waste the time. I can say only one thing. The only one thing which cannot be recycled is none other than wasted time. Okay. I wish you all the best and have a great weekend. Sunday, right? This is Abhiram signing off. Jai Hind.
Sir, I want that comment, sir.
Yeah, you will get it. You will get it. I understand. You want to know with respect to the tool.
Yes, sir. Comment for reading the file.
See, for to import the RTL code, you take read underscore SD, like read underscore HDL, and even if you want to generate it, is read underscore write underscore HDL only. And so if you want to like import the floor plan def, it could be some read underscore that particular design def, like that. It could be. It starts with read only, and I don't know much exactly.
Okay,
Okay.
sir.
So that is in terms of read only, I'm sure. Okay. Bye everyone.